talk is by Felice. TMS would like to tell us about track C filtering with convolutional analysis.
So, hello, I'm Felice Pantaleo. I'm working on future tracking and clustering at the CMS experiment. Today I'm going to do this talk on behalf of two weekly supervised students that worked this summer on a filtering, track seeding filtering at the CMS experiment for the high-level trigger. So just a little bit of introduction. So what you can see on the right is the average processing time of the CMS file as it against the average instantaneous luminosity, and as you can see, it's not going up linearly. It depends on basically on many on the fake rate that you can get in tracking. In fact, what you see is the distribution of the processing time, and you can see that there are two behaviors. One is very fast. In the first part, it's responding in less than 100 milliseconds. And if you start doing the part reconstruction, well, the timing starts increasing. In the worst case, timing increases the combinatorial of the pileup. Otherwise, it's in the best case scenario, you will get the quadratic of the pileup. So this means also that pixel tracks, which we use as a seed, cannot be evaluated for every event at the HLT. So just to give you an idea, this is the old actually CMS tracker, but what we are focusing on is the innermost part, which is the pixel detector, which is used in the online for pixel-only tracks for fast vertexing and tracking. Instead, in the offline, they are used as a seed, and then a Kalman filter is used for creating the tracks in the outer tracker. So we just upgraded the detector. So this is an X-ray rendering of the new detector. You cannot see, but there are 4 layers in the barrels. So here on the right, you see the new version compared to the old one. So you have 4 layers on the barrels and 3 end caps divided into rings each. So we have a completely new detector, and we use this opportunity to replace also the seeding at the pixel level. So if during the CMS phase 0, which ended for the pixel ended last year, we used to do triplets at the pixel track stage. Today we use quadruplets, and here you will find other iterations that we use. So I'm going to talk about the doublet generation. By doublet generation, I mean you have a hit on the outer layer, and you want to connect it on the innermost layer. This has become quite important with the phase 1 tracking, because the strategy that we are using today for track seeding at CMS is based on a hit chain maker based on a cellular automaton, which is basically creating doublets for all the possible combinations that you need to do for. It's basically creating a big graph for all the combinations of layers that you have, and you may find more details about this by my evil twin this afternoon in track 1 next session. Now, if you want to do pixel tracking and you are stuck with just geometrical information, you end up with a pileup with a lot of combinatorics, because in this search window you will find hundreds of hits. So an idea that we had is, why should we follow all the possible tracks if we can actually look at the shape of these pixels, of these pixel hits, which are actually clusters, and follow only those pixel hits which are compatible with each other. So this is the workflow that we have today at the CMS pixel tracking. So we basically have pixel kits, which are just clusters made of single pixels, adjacent pixels, and we create doublets for all the possible layer pairs, and then we run this cellular automaton and we fit the tracks. So what we want to do is go back to the doublet generation and start filtering pixel clusters based on their shape. So what you can see here is basically a heap. This is the representation of one particular hit in the barrel, and this is for the same track in the end cap. And you can see that they are quite different, but still they look somehow like images. So we tried we tried to apply a filter. The requirements for this filter are that it has to be basically 100% efficient. We don't want to reject any doublet, but we want to reject most of the fake doublets because this will kill completely the combinatorial downstream. So what we use as a training dataset is TT bar plus 35 pileup, and what we have observed, since we are imposing very loose cuts, so this doublet generation depends on the minimum PT that we allow. So we get quite a number of doublets. This is very unbalanced data set. So for each good doublet, you end up with 200 fakes. And this will basically explode with the combinatorial. So there are around, on average, 3,000 true doublets per event. And the association was done for the training. It was supervised. So the association was done by checking the hits which were matched to a simulated track in the reconstruction. But what we want actually to do is to pass into the network the position of the hit. What we just want to do is match two hits by their shape. So this is the input. So what we have is basically a matrix of 15 times 15, which contains completely the shape centered. The cluster is centered in this matrix, and we have two of them. Then we have a lot of labels because we want actually to see the behavior against all the different possibilities. We also normalize with the incident angle because by not having the position of the hit, this is an important information if you want to match two clusters together. So we explored two approaches. One is based on tuning on the detector. This means that you basically want to have three different networks, one for barrel-barrel combination, one for barrel end cap, and the last for two hits which belong to the end caps. And the other one is creating basically a single big network which contains all the features and contains all the layers and uses channels just like in RGB for getting all the positions of all the hits on the geometry of the detector. So we have also another problem, which is the fact that in our pixel detector we have frequent modules. So basically our detector is built on ladders, and one ladder has a normal position and the next one is frequent. This means that the electric field changes direction, and this means that it has another effect, a different effect on the Lorentz angle, making the shape a little bit different. So we have also to check on which ladder we are So this is the first attempt. For the detector approach, we have a concatenation of a CNN architecture. So we have a stack of 4 convolutional layers and 2 max pooling, and a dense architecture. So you have 2 dense layers which are fed with one-dimensional reduced images and doublet informations. So we have local information about the position of the detector. We apply dropouts to prevent overfitting, and training and validation datasets are balanced. So these are the results. Basically, we applied early stopping with the patients of 20 because it was already stable. You can see it was already stable already here after 50 epochs. And the rock curve is quite good. The area is almost 97%. So this also means that, again, it's a filter, but we don't want to filter the root doublets. So this means that if you want to reach an efficiency of 99%, you can actually reject almost 30% of the fake. And in the case of 300 fakes against one root doublet, is quite good. The feature layer map approach is basically different in the way that each layer has its own channel. So instead of getting a small number in the third dimension of the matrix, you get 24, which are 10 layers because you have 2 hits. So it's 20 plus 4 for the angular information. Again, this is again a concatenation of CNN architecture and dense architecture, and the results are here. So basically, this allows to have basically the same performance, the same physics performance, but with just one network. So you can get you just have to train on the entire event without selecting all the layers combination depending on barrel, and end cap. The physics performance again are quite good. So if you want to have an efficiency of 99%, the rejection is basically 34%, which is again welcome. So going to the conclusion, this is the first time that we apply deep neural networks on tracking, directly on tracking in CMS. We are exploring the integration of this in the CMS reconstruction framework. The CMS collaboration has successfully integrated TensorFlow. We are now in the position of starting to do inference directly in the CMS framework using different possible architectures. The verification of the effect of the downstream track reconstruction is ongoing. So what we expect is not, this is not where this network has the main effect. Because if you reduce the combinatorial, you will get less fake rate. The efficiency will be the same, but the purity will also increase, and the total time should also decrease. Also, and the other ongoing effort is the exploration of different hardware architectures. We just acquired some Intel FPGAs for doing fast inference, and we are going to test it. Thank you.
Do we have time for questions? Where do you intend to set the working point?
99 point something percent. Because
reduction rate of, let's say, 99.9%.
Sorry?
What's the reduction rate of
30%. 30%. Yes, 99%. It was 34%.
99.9.
I will let you.
99% is
32. No, I know. Yeah, we have to see also the effect on the downstream, because what we can, I mean, a bug that we can use as a feature in CMS is the fact that we have double layers. So if you remove one and you don't remove the other, you also kill the duplicate by not having 99.99% efficiency.
So what actually process, let's say, some 99.9% of the smaller efficiency, but what actually process any features, since you know the causal origins of those for combinatorics, or is this some overlap like a delta or something?
So the problem, so what I'm showing here is the efficiency and rejection of just this data. So as you know, in the reconstruction, we also apply geometrical filters. These are not considered. So maybe it's just
at some point it has a rejection.
Yeah.
What's passing?
I have not explored them.
Because it's complicated to assign what's real and what's not. Not getting secondary particles.